Hello and welcome. So in this video we are going to continue with the page 2. So in the previous video we derived these two equations and these ones, and now let's go and start reading from here. So after 3 seconds, a body that has been dropped from the rest has fallen a distance which is equal to this. So let's derive this equation. The equation is, so we have s, and change to this, okay, s is equal to 1 over 2 gt squared. The way it's derived is, okay, let's firstly write down the equation for displacement. So displacement is equal to the change in velocity. So let's write it as change in velocity, not change. Yeah, let's call change in velocity. Change in velocity times time. But because of the fact that the body was dropped from the rest, we can write the change in velocity as the average velocity through all the paths that this body is going to go, and so we can write it as the average velocity times time, right? And the average can be written out as final velocity plus initial velocity divided by 2 multiplied by t, right? Because of the fact that again the body is dropped from the rest, the initial velocity is going to be 0. Okay, it's going to be equal to 0. So in this case, the displacement is equal to v final divided by 2 multiplied by t. So if we are good with that, with this one, we can now what we are going to do right now is to do the same, but for an acceleration. The way that we define acceleration is the change in velocity over time, right? And again, the change in velocity is the v finals minus v initial divided by t, and but because of the fact that it's again from the rest, it's equal to 0, and v final, so acceleration is equal to v final divided by t. Okay, so in this case again we can write we can take vf out and write as v final is equal to a times t, so it's equal to a times t. When the body is dropped, it's subjected to an acceleration, to the gravitational constant, gravitational acceleration. So we'll consider a as g, okay, which stands for gravitational acceleration. So we can write this one as v final is equal to g times t, and then by simply putting this one right over here, we can get the equation for a drop-in object as z is equal to g times t divided by 2, which is equal to gt squared divided by 2. Okay, so this is for this one. Next one is the volume V of 3 grams of carbon dioxide at this temperature is given in terms of pressure and volume by this equation. So the equation is V is equal to 1.68 divided by P in atmosphere. So this one in atmosphere and this one in liters. Okay. So the first thing that we do is we should write down the Boyle's equation. The PV is equal to number of moles for gas, gas constants times temperature, and from there we can take V out and write as nRT divided by P equal to n, in our case number of moles, is equal to m divided by m, and m is 3 gram, right? Yes, 3 grams, divided by molar mass, it's 44, and this one is going to give us 3 divided by 44 is going to give us 0.068, 0.068, and it's going to be 0.068 times r, in terms of liter and atmosphere, 0.082 times T, which is 300 Kelvin, divided by pressure in atmosphere, okay, and because we have taken this Boltzmann the gas constant as in terms of liters and atmosphere. So from there on, V is going to be equal to 0.068 times 0.082 times 300, and is equal to 167 divided by P. Probably because of the fact that we approximated, there's a 1 unit difference. Okay, so we can go further. Definition of a function: a real valued function f defined on a set D of real numbers is a rule that assigns to each number x in D exactly one real number denoted by fx. The set D of all numbers for which fx is defined is called the domain or domain of the function of the function. The number f of x read is called the value of the function f at the number or point x. The set of all values y is equal to f of x is called the range of f. That is, the range of f is the set. This is the way that the function is denoted, right? And in this case, so just once again, when we are talking about function, there is certain inputs and certain outputs, and sometimes in a lot of different sources it's called a function machine. When there is we can visualize it as the machine which takes a certain inputs and gives certain outputs, and this inputs is called the domain, or x values in our case, domain of the function, and the output is in a certain range, okay, which is called the range of the function. It cannot give like all the output in the world. It can, because it takes a certain type of inputs. It takes gives away a certain outputs, or certain outputs in a certain range, which is called the range of the function. And here is a simple example. This squaring function defined as this one, assigned to each real number x is its square. So what we are doing is we are sending the inputs as x, and it gives us an output as x squared. For example, we are giving the value 3, it gives us 9, then 4, 16, so on and so forth. So and of course, because of it's a function, it has a certain domain which is equal to all the real numbers, okay? Because every real number can be squared, the domain of f is a set R of all real numbers, but only non-negative numbers are squares. So if we will say that a is more than or equal to 0, and take a square root of a and then square it, we will get the function of a square root of a. And because of the fact that this function is going to be equal to a, and we say that a is more than or equal to 0, we can say that the range of the output of this function is all the non-negative real numbers, okay, which is said right over here. Yeah, so the range of squaring function f is the set y more than or equal to 0 of all non-negative real numbers.